Tonight, we're going to figure out how long it would actually take us to travel 1 light year. It's one of the most basic units astronomers use for measuring the distance between stars. The first one you reach for once you leave our own solar system behind. Most people assume it's something within striking distance of our current technology if we simply pushed a little harder. But here's the thing most people don't realize. When you run the numbers honestly, accounting for every spacecraft we've ever launched, every propulsion concept anyone has seriously proposed, and every constraint the laws of physics impose on moving matter through space, 1 light year turns into something far harder to reach than it sounds. By the end of tonight, you're going to understand exactly why that distance has proven so difficult to close, and what it would genuinely take to finally get there. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with the number itself. A light year is not a measure of time, even though the name suggests otherwise. It's a measure of distance, specifically the distance that light travels in a vacuum over the course of 1 year. Light moves at approximately 186,282 miles per second. That's not an approximation for effect. That's close to the actual measured constant, one of the most precisely known numbers in all of physics. At that speed, light could circle the entire Earth about 7.5 times in a single second. Multiply that speed by the number of seconds in a year, roughly 31,556,000 seconds, and you get the distance of 1 light year, 5.87 trillion miles. That is the distance light covers in the time it takes Earth to complete 1 orbit around the Sun. And light doesn't pause. It simply moves. Constantly, at the fastest speed anything in the universe is permitted to travel. Nothing with mass can even approach that speed, a rule baked into the fundamental structure of reality itself. So when we ask how long it would take us to travel 1 light year, we're really asking a much more uncomfortable question underneath the surface. How far behind light are we, really? And the answer, as you're about to see, is almost embarrassing. Before we get to speeds and spacecraft, it helps to understand how we even came to know the speed of light in the first place, because for most of human history, nobody was even sure light had a speed at all. Ancient thinkers largely assumed light traveled instantly, appearing everywhere at once the moment a source was lit. It wasn't until the 1670s that a Danish astronomer named Ole Rømer, studying the moons of Jupiter, noticed something strange. The moon Io seemed to disappear behind Jupiter earlier or later than expected, depending on where Earth happened to be in its orbit around the Sun. Rømer realized the discrepancy wasn't a flaw in his calculations. It was because light itself took time to cross the changing distance between Earth and Jupiter. From that observation, he produced the first real estimate of the speed of light, a number in the right general range, though refined considerably by later scientists. Over the following 2 centuries, researchers like Hippolyte Fizeau and Albert Michelson developed increasingly precise laboratory methods, using spinning mirrors and toothed wheels to measure the tiny fraction of a second. It took light to travel a known distance and bounce back. By the early 20th century, the speed of light had been measured with remarkable accuracy, and it became one of the cornerstones of modern physics, eventually forming the backbone of Einstein's theory of relativity, which we'll return to later. It's a strange thought that something moving so unimaginably fast, fast enough to circle the Earth 7.5 times in a single second, still has a measurable, finite speed at all. But it does, and that finite speed is precisely what turns a distance like 1 light year from an abstract idea into a genuine physical barrier. Let's ground this in something familiar first, before we launch into the technical details. A commercial airliner, cruising at about 550 miles per hour, would need over 1,200,000 years to cover 1 light year. That's longer than the entire existence of our species on this planet, just to cover a distance that light casually strolls through in the time it takes you to watch this video and go about your normal week. Even the International Space Station, orbiting Earth at an impressive 17,500 miles per hour, fast enough to circle the entire planet in about 90 minutes, isn't fast enough. If it could somehow break orbit and fly in a straight line at that same speed, it would still need roughly 39,000 years to cover 1 light year. Everyday speeds are laughably inadequate for this task. We need something faster. Much, much faster. Decades of science fiction have quietly trained us to think of interstellar distances as casually crossable, a matter of dramatic music and a brief transition scene rather than years or centuries of travel. Fictional starships jump between star systems in moments. Crews chat comfortably with mission control in real time, regardless of distance. And a light year gets treated as barely significant compared to the truly vast distances those stories are built around. That framing is understandable, since a story about a multi-century journey to a single nearby star doesn't always make for gripping weekly television, but it leaves most people with a badly distorted sense of scale. When Jules Verne wrote about traveling to the moon in the 1860s, it took his fictional characters a matter of days, a wildly optimistic guess that nonetheless turned out to be roughly accurate once humanity actually made the trip about a century later. But the moon sits a little over 1 light second away, a distance so small compared to a light year that the comparison barely holds up at all. Scale that same optimism up to a full light year, and the gap between fiction and physical reality becomes enormous. Not a difference of years versus days, but a difference of years versus millennia, depending on which propulsion concept you're using as your baseline. None of this is meant to take anything away from science fiction, which has inspired generations of scientists and engineers to pursue careers in space exploration in the first place. But it does mean that when we ask a question like the one we're exploring here, how long would it really take to travel 1 light year? The honest answer requires setting aside the comfortable assumptions those stories have given us. It means looking directly at what physics and engineering actually allow. So, let's turn to the fastest things humanity has ever actually built and launched into space and see how they measure up. The Parker Solar Probe, launched by NASA in 2018 to study the Sun up close, holds the record as the fastest human-made object in history. At its closest approach to the Sun, using the star's own gravity to slingshot itself forward, the probe reaches speeds of around 430,000 miles per hour. That is an extraordinary achievement of engineering. A spacecraft moving fast enough to cross the entire continental United States in under 30 seconds. If you could maintain that speed indefinitely, aimed in a straight line toward deep space, how long would it take to cover 1 light year? The math works out to a little over 1,500 years. 1,500 years. using the fastest machine our species has ever produced. For context, 1,500 years ago, the Roman Empire in the West had only just fallen, and most of the technologies we take for granted today didn't exist in any form. That's the kind of timescale we're talking about, and this is our best spacecraft, under ideal and, frankly, unrealistic conditions. The Parker Solar Probe only reaches that speed by diving close to the Sun, and it would slow down dramatically once it left the Sun's gravitational influence behind. It's not actually built to maintain that velocity across open interstellar space. Voyager 1, the most distant human-made object ever launched, offers a more honest comparison because it actually is heading out of the solar system right now, coasting through interstellar space as we speak. Voyager 1 launched in 1977 and is currently traveling at about 38,000 miles per hour relative to the Sun. At that steady, sustainable speed, it would take Voyager 1 about 17,600 years to cover a single light year. 17,600 years. Voyager 1 launched in 1977, which means it has now been traveling continuously for close to 50 years, farther from Earth than any human-made object in history. And yet, after all that time, Voyager 1 has covered barely 2/1000ths of a single light year, a genuinely tiny fraction of the distance we've been discussing. If you scaled the full 1 light-year journey down to the length of a marathon, roughly 26 miles, Voyager 1's entire nearly 50-year journey so far would represent covering a little under 400 feet. There's a milestone happening in real time that puts this in perspective even further. In November of 2026, Voyager 1 is set to become the first human-made object in history to travel a full light day from Earth, a distance of about 16 billion miles, meaning a radio signal would need a full 24 hours just to reach it. It has taken Voyager 1 nearly 50 years of continuous flight to cover that single light day. A light year is 365 times farther than that. That comparison alone tells you almost everything you need to know about why this distance remains so far beyond our current reach. The Pioneer 10 and Pioneer 11 probes launched even earlier than Voyager in the early 1970s. They're moving even more slowly, and both have long since gone silent. Their radio transmitters grew too weak, and their power sources too depleted to communicate with Earth any longer. They're still drifting silently outward at speeds that would require roughly 25,000 years each to cover a single light year. They're still out there, coasting through the darkness. Each one carries a small plaque etched with images meant to represent humanity for whoever or whatever might one day encounter it. They're silent monuments to just how far a light year truly is, even for objects that have already been traveling for more than 50 years. For a sense of scale, agriculture itself, the entire foundation of human civilization, only began around 12,000 years ago. Voyager 1 would need longer than the whole of civilized human history just to cross the distance we're discussing, and that's assuming it kept its current trajectory and speed, uninterrupted, forever. New Horizons, the spacecraft that gave us our first close look at Pluto, moves at roughly 36,000 miles per hour, putting it in a similar range. It would need somewhere around 18,600 years to travel 1 light year. For comparison, the speed of sound, about 767 miles per hour at sea level, is the benchmark that supersonic aircraft like the retired Concorde, were built to exceed. Even the Concorde, cruising at around 1,350 miles per hour, over twice the speed of sound, would need just under 500,000 years to cover 1 light-year. Sound itself, if it could somehow travel through the vacuum of space, which it cannot, would need well over 800,000 years just to make the trip. And light still leaves it behind instantly, because light doesn't need a medium to travel through at all. There's a strange twist buried in this whole conversation. A single light year isn't just an abstract yardstick sitting somewhere out past the planets. It actually reaches into a region of our own solar system that we rarely think about, the Oort cloud. It's a vast, sparse shell of icy bodies believed to surround the Sun at distances estimated to extend out to somewhere between 1/2 and 1 full light year from where we're sitting right now. In other words, before a spacecraft heading outward even finishes covering 1 light year, it would still be, technically, inside the outer reaches of our own Sun's gravitational neighborhood. It would still be passing through a thin scattering of comets and icy debris left over from the formation of the solar system billions of years ago. That's a genuinely strange thing to consider. 1 light year, a distance that would take our fastest real spacecraft longer than the whole of recorded human history to cross, might not even get us fully clear of our own solar system's outer boundary. The Oort cloud itself is thought to contain trillions of icy objects, remnants left over from the earliest days of the solar system. Most of them are far too small and far too dim for any telescope to detect directly. Their presence is inferred instead from the long-period comets that occasionally fall inward toward the Sun, after being nudged loose by a passing star or a slight gravitational disturbance. And here's the uncomfortable truth. Every single spacecraft humanity has ever built, every triumph of engineering we've celebrated, every mission that made headlines around the world, he would need somewhere between 1,000 and 25,000 years just to cover this one modest unit of cosmic distance. And a light year, remember, is considered close in astronomical terms. The nearest star system to our own, Alpha Centauri, is over 4 light years away. We haven't even gotten there yet, and we're already talking about timescales longer than recorded human history. So the question becomes, could we build something faster? Something purpose-built for this exact challenge, rather than a probe designed to study planets or the Sun. Let's look at what's actually been proposed, and what stands in the way of each idea. Chemical rockets, the kind that have carried every human being who has ever left Earth, are fundamentally unsuited for this task. And it's not simply a matter of scaling up. Chemical rockets work by burning fuel and expelling the exhaust at high speed. And the maximum exhaust velocity you can achieve with chemical reactions is limited by the energy stored in the chemical bonds of the fuel itself. There's a hard ceiling there, set by chemistry, not by ambition or funding. The Saturn V rocket that sent astronauts to the Moon was one of the most powerful machines ever built, and even it could barely escape Earth's gravity, let alone approach any meaningful fraction of the speed of light. To reach even 1% of light speed, using chemical propulsion, you would need a mass of fuel so large it becomes physically nonsensical, because the fuel needed to accelerate. The fuel needed to accelerate the spacecraft grows faster than any rocket could carry. Engineers call this the tyranny of the rocket equation, and it's one of the most stubborn walls in all of aerospace engineering. The equation itself, first worked out by the Russian scientist Konstantin Tsiolkovsky in the late 1800s, describes a relationship that grows exponentially rather than in a straight line. To double a rocket's final speed using the same fuel and engine, you don't just need twice the fuel, you need dramatically more. That extra fuel itself has mass, and that mass has to be accelerated too, along with the fuel needed to accelerate it. It's a cascading requirement that spirals upward very quickly. For modest speeds, like the ones needed to reach orbit or travel to the moon, this relationship is manageable, which is exactly why chemical rockets have served us well for crewed spaceflight so far. But push the target speed high enough, even to a small fraction of the speed of light, and the required fuel mass grows so large that it would exceed the mass of entire planets, long before it exceeds the mass of anything an engineer could actually build and launch. This is precisely why every serious interstellar propulsion concept abandons the idea of carrying all your fuel with you from the start. Some harvest energy from nuclear reactions. Others draw on the near-total mass conversion of antimatter. Still others skip on-board fuel entirely in favor of an external push from a laser array, as with breakthrough Starshot. So chemical rockets are out, immediately and completely, for anything resembling a light-year journey within a human lifetime. What about nuclear propulsion? In the 1950s and 60s, a group of scientists and engineers worked on a genuinely audacious concept called Project Orion. The idea was to propel a spacecraft by detonating small nuclear explosives behind it, one after another, and absorbing the shockwave through a massive pusher plate, converting each blast into forward thrust. It sounds almost too dramatic to be real, but serious physicists worked on this for years, and computer models suggested it could theoretically push a spacecraft to somewhere around 3 to 5% of the speed of light. At 5% of light speed, a spacecraft could cover 1 light year in about 20 years. 20 years suddenly starts to sound almost reasonable, at least compared to 17,000 years. But Project Orion carried enormous problems. It would require detonating potentially thousands of nuclear devices, releasing radioactive fallout with every single pulse, at least during the portion of the journey still within the atmosphere or near Earth. International treaties banning nuclear detonations in space, put in place specifically because of concerns raised by this kind of concept, make Orion effectively illegal under current international law. The engineering challenges of building a pusher plate that could survive thousands of nuclear blasts without disintegrating were never fully solved either. Early Orion designs, worked on by physicist Freeman Dyson and his colleagues, imagined spacecraft weighing anywhere from a few thousand tons for smaller versions up to 8 million tons for the most ambitious interstellar variant. That version was sometimes called Orion Super. It was a vessel so massive it would have functioned less like a traditional spacecraft and more like a small, self-contained city hurled through space by controlled nuclear detonations. The interstellar version of the concept called for using hundreds of thousands of individual nuclear pulse units over the course of the acceleration phase. Each one would contribute a small increment of speed, gradually building toward that theoretical 3 to 5% of light speed over a period of months or years. Then the engines would shut down, and the vessel would simply coast for the remainder of the journey. Project Orion was quietly shelved. but it remains one of the more serious proposals for a propulsion system that could realistically approach a meaningful fraction of light speed using technology that isn't entirely speculative. Fusion propulsion represents another serious avenue, and it's the concept behind Project Daedalus, a study conducted by the British Interplanetary Society in the 1970s. The idea was to build a spacecraft powered by tiny pellets of fusion fuel, ignited in rapid succession by powerful lasers or electron beams, similar in principle to a continuous, controlled series of miniature fusion explosions inside a magnetic containment chamber. Fusion, the same process that powers the sun, releases far more energy per unit of fuel than any chemical reaction ever could. The Daedalus design, on paper, could theoretically reach around 12% of the speed of light. At that velocity, a spacecraft could cross 1 light-year in a little over 8 years. 8 years is genuinely within the range of a human mission, at least in theory, assuming a crew could survive the journey, which is a separate and enormous problem we'll return to shortly. The original Daedalus study envisioned an unmanned probe, not a crewed vessel, weighing around 54,000 tons at launch. The overwhelming majority of that mass was dedicated to fuel pellets, with only a tiny fraction reserved for the actual scientific payload and its instruments. The design called for a 2-stage engine. It would burn through the first stage over roughly 2 years to reach about 7% of light speed. Then it would jettison that stage and ignite a second stage for another 1.8 years, ultimately reaching that theoretical 12% figure. After that, it would coast the remaining distance in near silence, engines off, simply drifting at cruising velocity toward its target. Even scaled down and adapted for a crewed mission, which the original Daedalus study never actually attempted to design, the challenges remain daunting. The sheer quantity of fusion fuel required and the difficulty of igniting it in a controlled, sustained sequence rather than the theoretical pulse detonations the design called for remain well beyond current capabilities. The catch with fusion propulsion is that we still haven't achieved controlled, sustained fusion here on Earth in any practical, net positive energy form suitable for power generation, let alone a compact propulsion system light enough to fly on a spacecraft. Researchers have pursued controlled fusion for over 70 years, and while there have been genuine breakthroughs in recent years, including experiments that finally produced more energy than they consumed, we remain a considerable distance from a fusion-powered rocket engine. In December of 2022, researchers at the National Ignition Facility in California achieved a genuine milestone. Using an array of nearly 200 powerful lasers, they compressed a tiny fuel capsule and triggered a fusion reaction that produced more energy than the lasers delivered into the target. It was a result physicists had been chasing for decades. It was a real and significant achievement, confirmed and repeated in subsequent experiments. But it's important to be precise about what it actually demonstrated. The energy comparison only accounted for the energy delivered directly to the fuel capsule itself, not the much larger amount of energy consumed by the facility as a whole to power those lasers in the first place. Turning a result like this into a compact, self-sustaining fusion reactor, small and light enough to serve as a spacecraft engine, remains a substantially harder challenge. Most experts in the field still describe it as decades away, even with continued funding and research momentum following that breakthrough. Still, it represents genuine, measurable progress on a problem that had seen relatively little forward motion for much of the preceding half-century. It's exactly the kind of incremental step that eventually, cumulatively, closes the gap between theoretical propulsion concepts and working hardware. Antimatter propulsion is the most efficient, theoretical option physics currently allows, and the numbers involved are almost absurd. When matter meets antimatter, the two annihilate each other completely, converting 100% of their combined mass directly into energy. Following Einstein's famous equation, E equals mc squared. Chemical rockets convert a tiny fraction of 1% of their fuel's mass into usable energy. Fusion converts less than 1% of its fuel's mass into energy. Antimatter annihilation converts all of it. A spacecraft powered by antimatter could, in principle, approach a significant fraction of the speed of light. It could potentially reach 70 or 80% of light speed with a modest fuel mass. That would put a 1 light-year journey within a year or two of travel time, as measured by an outside observer. But producing antimatter is staggeringly difficult and staggeringly expensive. Our best particle accelerators can produce antimatter only in quantities measured in nanograms, and only at enormous energy cost, meaning we currently spend far more energy creating antimatter than we would ever get back from it. The total amount of antimatter humanity has ever produced across all of scientific history wouldn't be enough to power a household light bulb for more than a few minutes. Storing antimatter is its own nightmare, since it must never touch ordinary matter, or it reacts instantly and violently, meaning any storage system would require a flawless magnetic containment field, maintained without interruption for years at a time. One failure, one power interruption, one small malfunction, and the entire fuel supply releases its energy all at once, with consequences far more severe than any conventional explosion. Antimatter propulsion remains, for now, firmly in the realm of theoretical physics rather than engineering reality. Ion propulsion deserves a mention here too, mostly because, unlike several of the concepts we've already covered, it's technology we've actually used successfully on real missions today. Ion engines work by ionizing a gas, typically xenon, and using electric fields to accelerate those charged particles out the back of the spacecraft at very high velocity. The thrust is extremely gentle, often no stronger than the pressure of a piece of paper resting in your hand. But it's remarkably efficient, since ion engines use their fuel far more effectively than any chemical rocket. NASA's Dawn spacecraft used ion propulsion to visit and orbit 2 separate bodies in the asteroid belt. The technology has become a reliable workhorse for missions that can afford to accelerate gradually over months or years, rather than requiring the sudden, powerful thrust of a chemical rocket. The problem for a light-year journey is that even the most advanced ion engines currently available top out at exhaust velocities and thrust levels that would take many centuries of continuous operation, just to reach a small fraction of light speed. And the electrical power required to run an ion engine at that scale, for that long, would demand a power source, likely nuclear, far beyond anything currently designed for spaceflight. Ion propulsion is a genuine success story for exploration within our own solar system, but it simply isn't built for the kind of speed a light-year journey demands. One more idea captured the imagination of physicists for decades, called the Bussard interstellar ramjet, first proposed in 1960 by physicist Robert Bussard. The concept was elegant on paper. Interstellar space, though nearly empty, isn't perfectly empty. It contains a very thin scattering of hydrogen atoms drifting between the stars. Bussard proposed a spacecraft equipped with an enormous magnetic scoop, potentially hundreds of miles across, that would collect these stray hydrogen atoms as it moved forward, funneling them into a fusion reactor to generate continuous thrust. In theory, a ramjet like this could keep accelerating indefinitely, since it wouldn't need to carry its own fuel. It would simply harvest what it needed from the interstellar medium itself as it flew. Some early calculations suggested a Bussard ramjet could theoretically approach a significant fraction of light speed, given enough time to accelerate. Unfortunately, later, more detailed analysis revealed a serious problem. The density of hydrogen in interstellar space is so low that the drag created by the scoop itself, pushing against that thin gas, would likely produce more resistance than the fusion reaction could overcome in thrust, at least using realistic scoop designs. The concept hasn't been entirely abandoned by theorists, but it's now viewed as far less promising than it seemed when Bussard first proposed it. A reminder that even elegant ideas on paper often run into stubborn practical limits once the details are worked out. One more concept stands out as arguably the most promising near-term approach humanity has actually begun testing: solar sails and laser propulsion. A solar sail works on a simple principle. Light carries momentum, even though photons have no mass. When photons strike a reflective surface, they transfer a tiny amount of that momentum, producing a very small but continuous push. Japan's Ikaros spacecraft demonstrated this technology successfully in 2010, proving that solar sails genuinely work in practice, not just in theory. Since then, other missions have continued refining the concept. The Planetary Society's Light Sail spacecraft, a small crowd-funded mission, successfully demonstrated controlled solar sailing in Earth orbit. NASA has run its own solar sail projects too, exploring larger sail designs intended for deeper space missions. These missions test materials, deployment mechanisms, and navigation techniques that any future interstellar sail concept would eventually need to rely on. Each of these missions operates at a tiny fraction of the scale and ambition required for an interstellar laser sail. But they serve an essential purpose. They prove out individual pieces of the technology in a low-risk, low-cost environment before anyone commits to something as ambitious as a breakthrough Starshot-style mission. The problem with sunlight alone is that it weakens rapidly with distance, following an inverse square relationship. So a sail, relying purely on sunlight, loses most of its pushing power once it travels beyond the orbit of Mars. This is where a more ambitious idea comes in, one currently being studied under an initiative called Breakthrough Starshot. Instead of relying on sunlight, the concept proposes using an enormous array of ground-based lasers focused with extreme precision on a tiny, ultra-lightweight sail attached to a spacecraft weighing only a few grams. By concentrating enormous power into a coherent beam and firing it continuously at the sail for several minutes, researchers calculate you could accelerate a gram-scale probe to as much as 20% of the speed of light. At 20% of light speed, 1 light year would take just 5 years to cross. 5 years. That number should genuinely surprise you, because it's the fastest realistic figure we've encountered so far. And unlike some of the other concepts, the underlying physics doesn't require any breakthroughs we haven't already demonstrated in small-scale experiments. The challenge with Breakthrough Starshot isn't primarily the physics, it's the scale of engineering required. You'd need a laser array with a combined output measured in the tens of gigawatts, focused with such precision across such enormous distances that even tiny atmospheric distortions could scatter the beam and waste most of its energy. Proposed designs call for the array to be built at a high-altitude site with clear, dry, stable air. Even small amounts of atmospheric turbulence can bend and scatter a laser beam over the kind of distance it would need to travel before the sail leaves the immediate vicinity of Earth. Some concepts propose synchronizing thousands of individual smaller lasers, phased together with extreme precision to act as a single coherent beam. This offers redundancy, since losing a handful of individual laser units out of thousands wouldn't meaningfully reduce the total output. But it also multiplies the engineering complexity considerably. It requires the kind of precise timing and alignment across a huge physical area that has never been attempted at this scale. You'd need a sail thinner than a soap bubble, yet strong enough to survive the force of that beam without tearing apart. And crucially, this approach only works for tiny, unmanned probes weighing a few grams. That's nothing close to the mass of a spacecraft capable of carrying a human being, life support systems, food, water, and shielding. Scaling this concept up to carry passengers multiplies the required laser power by many orders of magnitude, well beyond anything currently conceivable with existing infrastructure or funding. Before we move away from propulsion concepts entirely, there's one more idea that comes up so often in popular culture, and that's the warp drive. In 1994, a Mexican physicist named Miguel Alcubierre published a paper describing a mathematically valid solution within Einstein's equations. It would allow a spacecraft to reach a destination faster than light would normally allow, without technically breaking the speed limit imposed by relativity. The idea isn't to accelerate the spacecraft itself to faster than light speeds, since that remains forbidden. Instead, the concept contracts space in front of the vessel and expands space behind it. The ship effectively rides a wave in the fabric of space itself, similar to how a surfer rides a wave rather than swimming through the water directly. Inside its own little bubble, the spacecraft wouldn't be moving faster than light at all, but the bubble itself could, in principle, cover enormous distances in very little time as measured by an outside observer. It's a genuinely fascinating piece of mathematics, and it briefly generated enormous excitement when it was published. But there's a serious catch, one that has kept the Alcubierre drive firmly in the category of theoretical curiosity rather than engineering roadmap. The math requires a form of matter with negative energy density, often called exotic matter, something that has never been observed to exist in the required quantities. And some physicists question whether it can exist in a usable form at all. Even setting that aside, early calculations suggested the amount of energy required would be roughly equivalent to converting the mass of an entire planet the size of Jupiter directly into energy. Later refinements to the concept have reduced that requirement considerably, without eliminating it. There are also unresolved theoretical problems involving what happens at the front and back edges of the warp bubble. There are open questions about whether anything could actually see out of it or navigate while inside it. And some physicists worry the concept might violate other fundamental principles of physics, even if the core equations are technically valid. For now, the warp drive remains a beautiful piece of theoretical physics. It shows just how creative, serious scientists have been willing to get in, searching for a loophole around the light speed barrier. But it isn't something you'll find on any realistic engineering roadmap for the coming decades, or possibly even centuries. So where does this leave us? We've looked at real spacecraft, the ones actually built and launched by NASA and other space agencies. Every single one of them needs somewhere between 1,000 and 25,000 years to cover this distance. Those timescales dwarf the entire span of recorded human civilization. We've looked at theoretical nuclear pulse propulsion, the Project Orion concept from the 1950s and 60s. It could potentially manage the trip in around 20 years, an enormous improvement. But it's bound up in serious radiation concerns, international treaty violations, and engineering problems that were never fully solved before the project was shelved. We've looked at fusion, propulsion, the Project Daedalus concept from the 1970s, hovering around 8 years for the crossing. It depends on a form of controlled fusion that remains, even after 70 years of dedicated research, just beyond our current capabilities. We've looked at antimatter propulsion, potentially the fastest and most efficient option of all, according to the raw physics. It's locked behind a production and storage problem so severe that all the antimatter humanity has ever created wouldn't power a light bulb for more than a few minutes. And we've looked at laser-driven sails, the breakthrough starshot concept, offering a genuinely plausible 5-year figure for a tiny unmanned probe weighing only a few grams. It's built on physics we've already demonstrated in small-scale experiments. Human transport at that same speed remains a vastly harder proposition, since mass, shielding, and life support requirements scale the challenge up by many orders of magnitude. We even looked at the Bussard interstellar ramjet and the Alcubierre warp drive, two of the more creative theoretical attempts to sidestep the problem entirely. Both run into serious, currently unsolved, physical obstacles that keep them firmly in the realm of speculation rather than engineering. It helps to ask what we'd actually gain scientifically from reaching this distance, even with an unmanned probe, because the answer explains why researchers consider the effort worthwhile at all. Voyager 1 and Voyager 2 have already given us our first direct measurements of the heliopause, the boundary where the sun's solar wind gives way to the pressure of the broader interstellar medium. That transition happens at roughly 120 times the distance from the Earth to the Sun, far short of a full light year. But it already gave scientists their first taste of genuinely interstellar conditions. A probe capable of reaching a full light year would travel roughly 500 times farther than that boundary, sampling the density, composition, and magnetic properties of interstellar space across a scale we've never directly measured before. This matters because our current understanding of the interstellar medium, the thin material that fills the space between stars, comes almost entirely from indirect observation. We watch light pass through it and get subtly altered along the way, rather than measuring it directly in place. A probe traveling a full light year could also test our models of the outer Oort cloud directly. It could potentially image or even pass near some of the icy bodies believed to populate that distant region. Those are objects far too faint and far too distant for any telescope on Earth or in Earth orbit to study in meaningful detail. There's also the simple, foundational value of validating the propulsion technology itself. Successfully accelerating any object, even a probe weighing only a few grams, to a meaningful fraction of the speed of light would be a genuine milestone. So would successfully tracking, communicating with, and controlling it across that vast a distance. Either achievement would immediately inform the design of larger, more capable missions that might follow. Notice something interesting here. None of these approaches, even the most optimistic and speculative among them, gets us there instantly, or even quickly by ordinary standards. Even in our best-case scenarios, we're talking about years of continuous travel using technology that ranges from barely developed to entirely theoretical. And this is for 1 light year. The nearest actual star system beyond our Sun sits over 4 times farther away than that. Not every proposal on the table is purely speculative or decades from any real hardware. NASA and several partner institutions have spent years studying a concept called the interstellar probe. It wouldn't attempt to reach another star at all. Instead, it would aim to travel farther from the Sun than Voyager 1 has managed, using more modern propulsion and a more direct trajectory. It could potentially cover meaningful ground toward the inner edge of that same Oort cloud region within a human career span. Proposed designs for this mission rely on a combination of a powerful conventional rocket launch, combined with a close solar gravity assist. This is sometimes called an O-berth maneuver, where a spacecraft dives close to the Sun and fires its engines at the point of maximum speed, using the Sun's own gravity to amplify the effect of the burn. Some versions of this concept could potentially reach speeds significantly higher than Voyager 1's current pace, though still nowhere near what would be needed to cover a full light year within a practical time frame. Nuclear thermal propulsion is another intermediate technology, sitting somewhere between chemical rockets and the more exotic fusion and antimatter concepts we've already covered. Rather than burning chemical fuel, a nuclear thermal engine uses a small onboard reactor to superheat a propellant, typically hydrogen, and expel it at velocities considerably higher than chemical combustion allows. NASA tested versions of this technology decades ago under a program called NERVA. Renewed interest in recent years has explored nuclear thermal engines as a way to dramatically cut travel times within our own solar system, potentially shortening a crewed mission to Mars by months. It's a genuinely useful technology for solar system travel. But even nuclear thermal propulsion falls dramatically short of what's needed for a light-year journey. It offers speeds only modestly higher than chemical rockets, nowhere near the fractions of light speed required to make an interstellar crossing survivable within a human lifetime. These nearer-term concepts matter because they represent the actual, funded, currently developing edge of propulsion technology, the stepping stones that come before anything resembling a true interstellar mission becomes possible. None of these nearer-term missions will cover anywhere close to a full light year. But each one tests a piece of the underlying engineering: faster trajectories, better power systems, more efficient use of gravity assists. Any future interstellar attempt would need to build upon that work rather than invent it from scratch. Now, let's shift gears and talk about something that changes this entire conversation in a strange and fascinating way: relativity. Albert Einstein's theory of special relativity tells us that as an object approaches the speed of light, time itself begins to behave differently for that object relative to an outside observer. This isn't science fiction. It's been measured and confirmed repeatedly, including with atomic clocks flown on airplanes and satellites, which run at very slightly different rates than identical clocks on the ground. The effect is called time dilation, and it becomes dramatically more pronounced as speed increases toward the speed of light. Here's what that means for our hypothetical light-year journey. If a spacecraft could somehow reach 80% of the speed of light, an external observer watching from Earth would calculate the journey taking about 1.25 years to cover 1 light year. But for the crew aboard that spacecraft, moving at that tremendous velocity, their own experience of time would pass more slowly relative to Earth. At 80% of light speed, time dilation means the crew would experience the journey as taking roughly 9 months instead of the full 1.25 years. An Earth observer would measure, push the spacecraft to 99% of the speed of light, an extraordinarily difficult target, but one physics doesn't forbid. And the external observer still measures just over 1 year for the trip. But the crew inside, thanks to relativity, would experience only about 7 weeks passing on their own clocks and calendars. This is one of the strangest and most genuinely mind-bending aspects of interstellar travel. The faster you go, the shorter the journey feels from the traveler's own perspective, even though observers left behind measure something much closer to the straightforward light-year figure. It's not an illusion or a trick of perception. It's a real, measurable difference in the passage of time itself, built into the structure of the universe. This is one of the few genuine loopholes physics offers us, a way to make interstellar journeys feel shorter for the people actually making them, even while the outside universe experiences something closer to the full duration. The catch, and there's always a catch, is that reaching these speeds requires propulsion technology far beyond anything we've discussed, and even beyond most of the theoretical concepts we covered earlier. The energy required to accelerate any object with mass toward these fractions of light speed increases dramatically the closer you get. It follows a curve that approaches infinity as you approach the speed of light itself. That's exactly why nothing with mass can ever reach that speed completely, only approach it. So relativity offers hope for the travelers, but it doesn't erase the fundamental engineering problem of getting to those speeds in the first place. This effect is sometimes called the twin paradox, a thought experiment where one twin stays on Earth while the other travels near the speed of light and returns. The traveling twin, upon returning, would find themselves younger than the twin who stayed behind. Not because of anything mystical. Time itself passed differently for each of them, depending on their relative speeds through space. It's called a paradox, mostly because it seems to violate common sense, not because it violates physics. It's been confirmed through real experiments too, including precise measurements of unstable particles that survive longer when moving at high speeds through particle accelerators than identical particles at rest, exactly as relativity predicts. Apply that same principle to our light-year journey, and something remarkable emerges. A crew traveling at a high enough fraction of light speed wouldn't just experience a shorter journey. They would return to find Earth had aged more than they had, assuming they made a round trip at all. It's a genuinely strange thing to imagine. A crew steps back onto Earth after what felt to them like only a handful of years, decades, or even longer, had passed for everyone and everything they left behind. Friends grown old, familiar cities transformed. An entire chapter of history unfolded in their absence, while their own calendars barely turned. At modest fractions of light speed, like the 12% theorized for a fusion-powered Daedalus-style spacecraft, this effect remains small, shaving only a small fraction off the crew's experienced time compared to Earth's clocks. But as speeds climb toward 50, 70, or 90% of light speed territory, we have no current technology capable of reaching. The gap between the traveler's experience and Earth's experience grows dramatically. That opens up genuinely strange possibilities for future generations, assuming propulsion technology ever advances that far. There's another relativistic effect that would fundamentally change what a crew traveling at a significant fraction of light speed would actually see through the windows of their spacecraft. At ordinary speeds, the stars ahead of you and behind you look roughly the way you'd expect, scattered points of light spread across the sky in familiar constellations. But as a spacecraft approaches a significant fraction of light speed, an effect called relativistic aberration causes the light from stars to appear to crowd forward, bunching up increasingly toward the direction of travel, while the stars behind seem to thin out and fade. At high enough speeds, this effect becomes so pronounced that nearly the entire visible sky would appear to compress into a bright ring or disk directly ahead of the spacecraft, with the space behind fading toward darkness. Combined with this, light from stars ahead would shift toward higher frequencies, an effect called blue shift. That could potentially push visible light into the ultraviolet range, making it invisible to human eyes without specialized instruments. Light from stars behind would redshift in the opposite direction, fading toward and eventually past the red end of the visible spectrum. In other words, a crew traveling fast enough to make a light-year journey survivable within a reasonable span of years might find themselves flying through a sky that looks nothing like the familiar starfield we're used to seeing from Earth. It's a genuinely alien view, and it exists as a direct, measurable consequence of moving close to the speed of light, not as some artistic embellishment. It's one of the more beautiful and strange predictions of relativity, and it's one more reminder that the closer you get to the speed of light, the more the universe itself starts to look and behave in ways that have no equivalent in ordinary human experience. Now, let's talk about what this journey would actually mean for the people who might attempt it, because even in the best-case scenarios we've discussed, we're still talking about years, not days or hours. A 5-year unmanned probe journey, like the one theorized under Breakthrough Starshot, involves no human survival concerns, since nothing living is aboard. But any crewed mission, even one that somehow achieved the more optimistic timelines we've discussed, would face enormous challenges that have nothing to do with propulsion physics and everything to do with human biology and psychology. Radiation exposure is one of the most serious concerns. Outside the protective shield of Earth's magnetic field, spacecraft and their crews are exposed to cosmic radiation, a steady stream of high-energy particles originating from the Sun and from sources deep in the galaxy. Over months and years, this radiation exposure increases the risk of serious, long-term health problems, and shielding against it effectively would require substantial mass, which directly conflicts with the need to keep a spacecraft as light as possible for speed and efficiency. Engineers working on interstellar concepts describe this as one of the most stubborn, unsolved problems in the entire field. A genuine engineering contradiction between the need for speed and the need for protection. There are actually two distinct types of radiation a crew would need to contend with, and they behave quite differently. Solar particle events are bursts of charged particles thrown off by the sun during periods of intense activity. They're dangerous, but at least somewhat predictable and localized, since their intensity drops off considerably with distance from the sun. That offers some relief the farther a spacecraft travels from home. Galactic cosmic rays are a different problem entirely. They originate from exploded stars and other violent events scattered across the galaxy, and they arrive from every direction at extremely high energies. They remain a constant background hazard, no matter how far a spacecraft travels from the sun. These galactic cosmic rays are particularly difficult to shield against. At their highest energies, they can pass through several feet of solid material, including the kind of aluminum or polyethylene shielding commonly used on spacecraft today. Sometimes they even produce secondary radiation as they interact with the shielding itself, a phenomenon engineers have to account for rather than ignore. Some proposed solutions involve active shielding, using powerful magnetic fields generated by the spacecraft itself to deflect charged particles before they ever reach the hull. It's a small-scale version of the same kind of protection Earth's own magnetic field provides against the solar wind. Researchers have tested small-scale prototypes of this kind of active shielding technology in laboratory settings, generating magnetic fields strong enough to noticeably deflect charged particle beams. Some concepts propose using superconducting magnets, cooled to extremely low temperatures, to generate the kind of sustained, powerful magnetic field a full-scale shield would require without consuming prohibitive amounts of electrical power. The engineering challenge lies in generating a field strong enough and shaped correctly enough to protect the entire crew compartment. At the same time, the mass and power requirements of the shielding system itself have to stay low, or it defeats the purpose by making the spacecraft too heavy to accelerate to meaningful speeds in the first place. It's a balancing act that remains unresolved for anything beyond small-scale laboratory demonstrations. Active magnetic shielding remains an active area of research, promising in theory, but not yet proven, at the scale or power levels a genuine interstellar mission would require. Isolation is another enormous factor. Even a 5 to 20-year journey, spent in a confined, artificial environment, far from any other human contact beyond the crew itself, places enormous psychological strain on the people involved. Studies of long-duration missions on the International Space Station, along with research into extended isolation in environments like Antarctic research stations, consistently show the same thing. Confinement, monotony, and separation from Earth take a genuine toll on mental health, even over periods measured in months rather than years. Researchers studying crews at isolated Antarctic outposts, particularly during the long polar winter when outside travel becomes impossible for months at a time, have documented a recognizable pattern. It's sometimes called the third quarter phenomenon, a dip in mood and cohesion that tends to appear roughly 2/3 of the way through an extended isolation period. Once the initial adjustment has worn off, but the return home still feels distant. Space agencies have used these findings to inform crew selection, training, and support protocols for missions on the International Space Station. And the same body of research forms much of the foundation for how mission planners think about the psychological demands of a much longer journey, one lasting years rather than months. Some proposals for genuinely long-duration missions include rotating crew responsibilities deliberately, building in scheduled private time, and designing living spaces with enough variety and personalization that the environment doesn't feel quite as relentlessly uniform day after day. These are small design choices, but research suggests they can meaningfully ease the psychological burden of extended confinement. Now, extend that experience to 5, 8, or 20 years, sealed inside a vessel with no possibility of turning back. No fresh air. No changing scenery beyond a starfield that barely shifts from day to day. The psychological demands become extraordinary. Crews on a mission like this would need to solve their own medical problems. They'd have to manage interpersonal conflicts in an environment with no escape and no privacy in any traditional sense. And they'd need to maintain morale and purpose across a span of time that, for a fusion-powered ship traveling at 12% of light speed, would represent nearly a tenth of an average human lifespan spent entirely inside a metal hull. Picture what that actually looks like from the inside for a moment. Selecting a crew for a mission like this would look very different from selecting astronauts for a mission to the Moon or Mars, where a return home within months or a couple of years remains the expectation. Mission planners, studying long-duration crewed concepts, have suggested that ideal candidates would need more than technical competence and physical health. They'd need an unusually stable temperament, strong conflict resolution skills, and a documented ability to sustain motivation and purpose over years without external novelty or change. Those qualities are considerably harder to test for than the physical fitness standards used for shorter missions. Some proposals even suggest selecting entire family units or established small communities rather than individually selected specialists. The theory is that pre-existing social bonds and support structures might prove more resilient over a multi-year journey than a crew of strangers brought together purely for their professional qualifications. Whichever approach any real mission eventually took, the selection process itself would likely take years. It would involve extensive psychological evaluation, simulated isolation tests, and close observation of how candidates handle sustained stress, conflict, and monotony, long before any of them ever set foot on an actual spacecraft. Picture a crew of engineers, scientists, and specialists, carefully selected and trained for years beforehand. They're sealed into a vessel barely larger than a small apartment building, watching Earth shrink from a blue marble to a faint point of light, indistinguishable from any other star within the first few months of the journey. The early excitement of launch fades within weeks. What replaces it is routine. The same corridors, the same recycled air carrying the same faint metallic smell, the same faces at every meal, day after day, for years without interruption. Small conflicts that would be forgettable on Earth, a disagreement over schedules, an irritating habit, a difference in temperament, take on outsized weight in an environment with no way to simply step outside and get some distance. Mission psychologists studying long-duration spaceflight already know that crew dynamics shift in predictable but difficult ways over extended isolation. Periods of heightened tension often appear around the midpoint of a mission, once the novelty has worn off, but the end still feels impossibly far away. For an 8 or 20-year journey, that midpoint crisis wouldn't be a matter of weeks. It would stretch across years, testing the patience, discipline, and resilience of everyone aboard in ways no training program on Earth could fully simulate in advance. And yet, history suggests people are capable of extraordinary endurance under exactly these kinds of conditions, provided they have purpose, structure, and a genuine sense that what they're doing matters. Crews would likely develop their own rituals and traditions along the way. Small ceremonies marking anniversaries of the launch. Birthdays celebrated with whatever ingredients the ship's food systems could produce. Quiet moments set aside for remembering Earth and the people left behind. These small acts of meaning-making aren't a footnote to the mission. They'd be as essential to its success as the propulsion system or the life support hardware. A spacecraft can be engineered to survive the vacuum of space, but a crew has to be prepared to survive years of their own minds, turned inward, with nowhere else to go. There's an alternative approach that researchers have seriously studied as a way to sidestep much of this psychological burden entirely. Inspired by the way some animals survive harsh conditions through hibernation. The idea is sometimes called torpor-induced travel. It would involve lowering a crew member's body temperature and metabolic rate significantly, placing them into a deep, medically induced sleep-like state for extended portions of the journey. That would reduce their need for food, water, oxygen, and psychological stimulation all at once. NASA has funded early-stage research into this concept, drawing on observations of animals like ground squirrels and bears that naturally enter states of dramatically reduced metabolism for months at a time without apparent harm. If a technique like this could be safely adapted for human physiology, it could transform the psychological calculus of a multi-year journey considerably. And that remains a considerable if, given how much we still don't understand about safely inducing and reversing deep torpor in humans. A crew could potentially experience only a fraction of the mission's actual duration while conscious, waking periodically for maintenance and monitoring before returning to a dormant state. Early experiments have shown some promise using lower body temperatures and pharmacological approaches, but nothing close to the multi-year dormancy periods a genuine interstellar mission would require has been demonstrated safely in humans. Significant medical hurdles remain too, including concerns about muscle and bone loss, potential neurological effects, and the basic challenge of safely lowering and later restoring core body temperature over such an extended period without complications. For now, hibernation remains a promising research direction rather than a solved problem. One more example of a concept that could meaningfully change the human factors calculation of interstellar travel, if the underlying medical science eventually catches up to the idea. Food and resource management present their own puzzle. A journey lasting even 5 years would require an enormous quantity of food, water, and breathable air. That is, unless the spacecraft incorporated a closed-loop life support system capable of recycling waste, growing food, and regenerating breathable atmosphere indefinitely. Such systems exist in early prototype form today, tested on stations like the ISS, but achieving a truly closed-loop system with zero net loss over years of continuous operation remains an unsolved engineering challenge. Current life support systems on the International Space Station recycle a substantial majority of water used aboard the station, reclaiming moisture from the air, from sweat, and even from urine, processing it back into drinking water through multiple filtration stages. Even with those systems, the International Space Station still relies on periodic resupply missions from Earth. Those missions replace air, water, and materials lost through small inefficiencies in the recycling process. That's a luxury that simply wouldn't exist for a spacecraft years or decades away from the nearest resupply point. A genuinely closed-loop system for an interstellar mission would need to recover essentially all of its water, oxygen, and a meaningful share of its food production internally, indefinitely, with no external supply chain to fall back on if something goes wrong. No system built so far has come close to fully achieving that over multi-year timescales. Growing food aboard a spacecraft presents its own set of complications. Plants require light, water, nutrients, and a stable environment, and all of that has to be provided artificially in a sealed vessel with no natural sunlight beyond what reaches it from distant stars. Experiments aboard the International Space Station have successfully grown small quantities of lettuce, radishes, and other crops in specially designed growth chambers. That's proof of concept that plants can survive and even thrive in microgravity. But scaling that up to provide a meaningful portion of a crew's caloric needs across a multi-year journey remains a substantially harder engineering problem. One that would likely require a spacecraft design built around agriculture almost as much as around propulsion. Any imperfection in that recycling loop compounds over time, meaning small inefficiencies that seem trivial on day one could become serious by year 3 or 4 of the journey. There's a hazard here that rarely gets enough attention in popular discussions of interstellar travel, and it involves something as unassuming as dust. Interstellar space contains scattered grains of dust and tiny particles, remnants from exploded stars, and the slow churn of galactic material over billions of years. At everyday speeds, a spacecraft could pass through this material without any concern at all. The particles are so sparse and so small that collisions are exceedingly rare and essentially harmless. But at even a modest fraction of the speed of light, the physics changes entirely. Kinetic energy increases with the square of velocity, meaning a particle that would be harmless at ordinary spacecraft speeds becomes something closer to a small explosive impact at relativistic speeds. A grain of dust weighing a fraction of a gram, striking a spacecraft traveling at 10 or 20% of light speed, would release an amount of energy comparable to a small artillery shell, concentrated into a single microscopic point of impact. To put a number on it, a dust grain weighing just 1 milligram, far smaller than a grain of sand, striking a spacecraft traveling at 20% of light speed would carry a kinetic energy comparable to several hundred pounds of TNT. That's far beyond a hand grenade, closer to a small truck bomb. And all of it would be delivered instantaneously to an area smaller than the head of a pin. Multiply that by the sheer number of such particles scattered across even a sparse light year of interstellar space. The cumulative probability of at least one significant impact over a journey lasting several years becomes a genuine mission risk. Shielding, redundant systems, and careful trajectory planning can reduce that risk, but not entirely eliminate it. Engineers studying concepts like breakthrough starshot have had to seriously consider shielding. Even then, A sustained journey of several years at high speed carries a real, cumulative risk of a strike serious enough to damage or completely disable a probe, let alone a crewed vessel carrying fragile life support systems and human passengers. Some proposed solutions involve a sacrificial shield made of a thick, disposable material at the front of the spacecraft, designed to absorb and vaporize incoming particles before they reach anything critical. It's similar in principle to the Whipple shields already used on the International Space Station to protect against micrometeorites, just scaled up dramatically to handle far higher impact energies. This is one of those problems that sounds almost trivial, a bit of cosmic dust, and yet turns out to be one of the more serious engineering obstacles standing between us and any spacecraft capable of moving fast enough to make a light-year journey worthwhile. And then there's the return question, one that rarely gets asked but deserves consideration. If a crew traveled 1 light-year outward, using one of these speculative propulsion systems, would they have any realistic path home? The fuel and energy required for the outbound journey are already at the ragged edge of what's theoretically achievable. Doubling that requirement for a return trip, or requiring an entirely separate refueling and launch infrastructure at the destination, adds a layer of complexity that most serious interstellar mission concepts simply treat as a one-way journey, at least for the first attempts. That's a sobering thought. There's another consequence of distance that has nothing to do with propulsion at all and everything to do with communication. Radio signals, like light itself, travel at the speed of light, which means any message sent from a spacecraft 1 light-year away would take a full year to reach Earth, and any reply sent back would take another full year to arrive. A simple question-and-answer exchange, something that takes seconds in an ordinary conversation, would take 2 full years from the moment the question was asked to the moment the answer was heard. Mission Control couldn't respond to an emergency in real time. They couldn't offer guidance through a sudden crisis. They could do nothing except wait and hope and trust that whatever training and equipment the crew carried with them would be enough to handle whatever came up along the way. This is a genuinely different kind of isolation than anything astronauts have experienced so far. Even the Apollo astronauts on the Moon, at their most distant, were only about 1.25 seconds away from Earth by radio. That allowed something close to a normal, if slightly delayed, conversation. A crew 1 light-year from home would exist in a kind of communication silence, unlike anything in the history of human exploration, sending messages into a year-long void and waiting patiently for whatever came back, if anything came back at all. Every serious proposal for reaching even this relatively modest distance of 1 light-year, using technology at the very edge of what physics permits, effectively describes a one-way trip. It would be made by people who would spend years of their lives, and quite possibly the remainder of their lives, traveling somewhere that Earth itself would only ever see as a message. A data transmission crawling back home at the speed of light itself. Now, let's put this whole conversation into a broader perspective, because it's easy to lose sight of the bigger picture once we start talking about fusion engines and antimatter storage and time dilation. 1 light-year, 5.87 trillion miles, is a genuinely enormous distance by any ordinary human measure. And yet, in the context of the universe we actually inhabit, it's remarkably small. The nearest star system to our own sun, Alpha Centauri, sits just over 4 light-years away. Our own galaxy, the Milky Way, stretches across roughly 100,000 light-years from end to end. Even our fastest theoretical propulsion concepts, the ones that could cross a single light-year in 5 to 20 years, would still need somewhere in the range of 500,000 to 2 million years to cross the galaxy in a straight line. And that's without accounting for the fact that a straight-line journey wouldn't even make sense given how the galaxy's spiral structure and rotation actually work. The nearest large galaxy to our own, Andromeda, sits about 2,500,000 light-years away. That's a distance so far beyond anything we've discussed so far that even expressing it in terms of our fastest theoretical propulsion concepts produces numbers stretching into the tens of Brate. Millions of years. That's longer than the entire existence of the genus that modern humans belong to. Astronomers currently estimate the observable universe contains somewhere in the range of 2 trillion galaxies. Each one contains anywhere from millions to hundreds of billions of individual stars. All of it is scattered across a universe that has been expanding for roughly 13,800,000,000 years, since the event we call the Big Bang. 1 light-year already requires timescales longer than recorded human civilization, using our fastest real spacecraft. It requires years of continuous travel, even using our most optimistic theoretical propulsion concepts. So the true scale of the observable universe becomes almost impossible to hold in perspective at all. We are, in a very real sense, profoundly local creatures. We're confined not just to our own planet, but effectively to our own solar system, at least for the foreseeable future of our technological development. Here's a detail that surprises a lot of people when they first hear it, and it directly touches on the distance we've spent this whole video discussing. As far as astronomers currently know, there is no confirmed star, planet, or other major object located within 1 light-year of our Sun. Nothing, other than the objects belonging to our own solar system, including that distant, sparse edge of the Oort cloud we mentioned earlier. The nearest confirmed star system, Alpha Centauri, sits over 4 times farther away than the distance we've been exploring here. That said, astronomers can't completely rule out the possibility of something small, dim, and previously undetected lurking closer than that. Objects called rogue planets, worlds that formed around a star and were later ejected by gravitational interactions, can be extraordinarily faint and difficult to detect, even relatively close by. So can brown dwarfs, failed stars too small to sustain the kind of fusion that powers a true star. Surveys using infrared telescopes have searched for exactly this kind of hidden nearby object for years, without finding any confirmed candidate within 1 light-year. The search continues, though, and the outer reaches of our galactic neighborhood remain less thoroughly mapped than most people assume. For now, though, the honest answer is that 1 light-year of travel in any direction from our Sun would take a spacecraft through a whole lot of nothing. An increasingly sparse scattering of icy debris, thinning out into the genuine emptiness of interstellar space, without reaching another star system at all. This is part of why so much of modern astronomy focuses on studying distant stars and planets from right here at home, rather than waiting for a spacecraft capable of visiting them directly. Space telescopes like the James Webb Space Telescope and earlier missions like the Kepler and TESS observatories have identified thousands of confirmed planets orbiting other stars. Most of them sit dozens, hundreds, or thousands of light years away, studied entirely through the light that reaches our instruments here, on or near Earth. These telescopes can measure a planet's size, estimate its temperature, and in some cases even analyze the chemical composition of its atmosphere, all without a single spacecraft ever leaving our own solar system. The technique typically involves watching a planet pass in front of its host star from our vantage point on Earth. Scientists analyze how the star's light changes as it filters through the thin sliver of that planet's atmosphere on the way to our telescopes. That method has already revealed the presence of water vapor, carbon dioxide, and other molecules in the atmospheres of planets many trillions of miles away. It's a genuinely remarkable achievement, extracting detailed information about worlds so distant that even our fastest theoretical propulsion concepts would need many thousands of years just to reach the nearest of them. But there's a meaningful difference between studying a world through light that took years or centuries to reach us and actually sending something there directly. That difference is exactly what makes the propulsion question we've spent this whole video exploring so significant, even for a distance as comparatively modest as a single light year. Every star you've ever looked at in the night sky, every point of light scattered across the darkness, sits at a distance that dwarfs the challenge we've spent this entire video exploring. It's a reminder of just how vast the gap remains between where our engineering currently stands and where our curiosity keeps pointing us. We've covered the sheer difficulty of radiation, isolation, resource management, and the risk posed by even a single grain of dust at high speed. Given all of that, there's one question mission planners take very seriously. Why send a human crew at all, when an unmanned probe could make the same journey without any of these survival concerns? There's real merit to this argument, and it's part of why concepts like Breakthrough Starshot focus specifically on tiny unmanned probes rather than crewed vessels. A probe doesn't need food, water, breathable air, radiation shielding thick enough to protect a fragile human body, or any of the psychological support systems a long-duration crew would require. A probe can be built dramatically lighter, accelerated dramatically faster, and risked without any question of loss of life if something goes wrong along the way. For pure scientific data collection, gathering close-up measurements of whatever lies at the far end of a light-year journey, an unmanned probe is almost certainly the more practical near-term approach. It's the approach every serious current proposal is actually built around. The case for sending humans specifically is less about efficiency and more about something harder to quantify. It's the desire to actually be there, to experience a place directly rather than only through instruments and data streams relayed back over the course of a year. Many people working in this field believe that human presence carries a kind of significance that no probe, however sophisticated, can fully replace. Whether that belief justifies the enormous additional cost, risk, and complexity of a crewed mission remains a genuinely open question, one that will likely be debated for decades before any serious crewed interstellar mission is ever actually attempted. And yet, there's something worth holding on to here, something that doesn't get erased by these humbling numbers. A single light year, once considered by earlier generations to be an almost mythical, unreachable distance, has now been meaningfully addressed by real engineering concepts. We're not simply throwing up our hands and declaring it impossible. We have real proposals, tested in small-scale experiments, fusion pellets, laser arrays, and solar sails thinner than soap film. They all point toward genuine paths forward, even if those paths remain difficult, expensive, and decades or centuries from actual implementation. The Parker Solar Probe, moving faster than any object humans have ever built, was itself unimaginable technology only a century ago. Voyager 1, still transmitting data from interstellar space after nearly 5 decades of continuous operation, represents a level of engineering endurance that would have seemed like fantasy to the earliest rocket scientists. Voyager 1 also carries a golden record bolted to its side, containing recordings of sounds and images from Earth, greetings recorded in dozens of languages, and music selected to represent something of what it means to be human. It was never expected to be found or heard by anyone, human or otherwise, certainly not within any time frame relevant to the people who built it. At Voyager's current speed, it would take that spacecraft roughly 17,600 years just to cover the single light year we've been discussing, and many tens of thousands of years beyond that before it passes anywhere near another star system at all. And yet, the record is there anyway. A message sent outward with no expectation of an answer. A small act of hope embedded in a piece of engineering hardware, drifting through the same kind of vast, empty distance we've spent this entire video trying to put into perspective. It's a fitting symbol for our topic. It captures something true about the entire project of interstellar exploration. The distances involved are so enormous, measured in years and decades and centuries, even under our most optimistic technological assumptions, that much of the effort has to be justified by something other than a guarantee of success within any single human lifetime. Progress in propulsion technology has been slow and incremental, but it has been steady, and there is no fundamental law of physics that says a light year, or even many light years, must remain forever beyond our reach. What stands between us and that first successful journey isn't some impossible barrier written into the fabric of the universe. It's engineering, funding, political will, and time. Those are the same obstacles that have stood between humanity and every great achievement in our history, from crossing oceans in wooden ships to walking on the surface of the moon. Funding in particular deserves a moment of honest attention. The propulsion concepts we've discussed aren't primarily held back by a lack of good ideas. They're held back by the sheer scale of investment required to move from a promising theory to a working, tested piece of hardware. The Breakthrough Starshot Initiative, one of the more actively funded interstellar concepts currently in development, has received substantial private funding to explore its core technologies. Yet even its own project timeline acknowledges that a genuine attempt at the full mission remains decades away, contingent on sustained investment and continued technical progress across dozens of separate engineering challenges simultaneously. Government-funded space programs, meanwhile, tend to operate on budget cycles measured in single years. That makes it genuinely difficult to sustain the kind of multi-decade, high-risk research program a serious interstellar propulsion effort would likely require. Political priorities and funding levels can shift dramatically from one administration or one budget cycle to the next. This is part of why so much of the most ambitious interstellar research today happens through a patchwork of university laboratories, private philanthropic funding, and small-scale government research grants. It's rather than through a single unified national program with guaranteed long-term support. That structure makes steady progress possible, but it rarely produces the kind of dramatic, headline-grabbing breakthroughs associated with programs like Apollo. Every one of those achievements once seemed just as far out of reach as an interstellar journey feels today. Sailors who crossed open oceans centuries ago had no guarantee of what lay beyond the horizon, no certainty of return, no modern navigation tools to guide them. Yet they went anyway, driven by curiosity, ambition, and the simple, stubborn desire to know what was out there. In the 1400s, a voyage across the Atlantic Ocean, a distance of a few thousand miles, represented the absolute edge of what was considered survivable. It was undertaken in wooden ships, with no reliable way to determine longitude, no weather forecasting, and no means of calling for help if something went wrong. Sailors of that era set out on journeys lasting weeks or months into genuinely unknown territory, carrying only the food, water, and equipment they could physically fit on board. They were fully aware that a significant percentage of ships attempting long voyages never returned at all. By the turn of the 20th century, expeditions were pushing into polar regions, into the Antarctic and Arctic. Those environments were so hostile that entire crews sometimes spent years trapped in ice, rationing supplies and relying on nothing but their own resourcefulness and endurance to survive until conditions allowed them to continue or return home. Each of these eras had its own version of the light-year problem, a distance or environment that seemed to sit right at the outer edge of what human technology and human endurance could possibly manage. It required not just better tools, but people willing to spend years of their lives, and sometimes their entire lives, pushing that boundary outward by however small a margin they could manage. The engineers and physicists working today on fusion propulsion, laser sail concepts, and antimatter containment are, in a very real sense, continuing that same tradition. They're just aimed outward into a darkness far vaster than any ocean, working on a boundary measured not in miles or months, but in trillions of miles and potentially thousands of years, unless something changes. Let's also consider something that often gets overlooked in conversations like this, which is what we might actually learn along the way, long before any spacecraft covers the full distance of a light year. Every incremental improvement in propulsion technology has applications much closer to home. Faster ion engines mean quicker missions to Mars and the outer planets. Better radiation shielding means safer, longer duration missions for astronauts working within our own solar system. Improved, closed-loop life support systems mean more sustainable outposts on the Moon or Mars, places we're already actively planning to build in the coming decades. Advances in laser array technology, originally driven by concepts like breakthrough starshot, have applications in communication, in planetary defense against asteroids, and in power transmission. A sufficiently powerful, precisely aimed laser array, the same kind of technology required to push an interstellar sail, could theoretically also be used to nudge a threatening asteroid off a collision course with Earth. It could vaporize surface material to create thrust in the opposite direction, or simply illuminate the asteroid with enough sustained energy to alter its trajectory gradually over time. That application has drawn direct interest and funding from planetary defense researchers, independent of any interstellar ambitions. Similarly, the same phased array techniques being explored for beaming power to a distant sail have parallel applications in beaming power between satellites. They could potentially even beam power from orbital solar collectors down to receivers on Earth, a concept researchers have studied for decades as a possible source of continuous, weather-independent, clean energy. In other words, the pursuit of a light-year journey drives real, tangible progress that benefits space exploration far closer to home, long before anyone ever attempts the full interstellar leap. That's true, even if the full crossing remains generations away. Consider the materials, science alone. Building a sail thin enough and light enough to be accelerated by laser light to a meaningful fraction of light speed requires developing materials that are simultaneously stronger